Welcome back to the course of chemical crystallography. In the previous couple of lectures, we have discussed about the direct method and the mathematical background, little bit of different methods, and then we talked about the practical way of doing the phase determination. The other method of structure solution was introduced by Patterson, and this is based on the presence of a heavy atom in the lattice. So, this Patterson map is calculated with the square of structure factor amplitudes and a phase of 0. This is an interatomic vector map that we will generate, and in this each peak corresponds to a vector between two atoms in the lattice. So, we will also have the self vectors coming at the origin. So, the peak intensity is defined as the product of electron densities of each atom. So, the Patterson function, that PUVW, is defined as this expression 1 by V sum over FHKL mod of FHKL square cos 2 pi HU plus KV plus LW. You can see that we just have the cos term, which indicates that the Patterson map is always centrosymmetric. In case of this Patterson map, he showed that the position of a peak at the coordinates u, v, w provided by this function corresponds to a vector between two atoms located at x1, y1, z1 and x2, y2, z2 in such a way that u equal to x1 minus x2, v equal to y1 minus y2, w equal to z1 minus z2 and the opposite vectors as well. So, suppose if we have n atoms in the unit cell, then we will have n square vectors in a Patterson map. How? Suppose we have 4 atoms like this. So, the Patterson map will have the vector peaks from atom 1 to atom 1. This is the self vector, and the other vectors 1 to 2 and 2 to 1, the opposite vector, 1 to 3 and 3 to 1, 1 to 4 and 4 to 1. Like that, we should have 2 to 2, the other self vector, 2 to 3 and 3 to 2, 2 to 4 and 4 to 2, and you should have 3 to 4 and 4 to 3. So, we have in addition 3 to 3 and 4 to 4. So, what we see, there are 4 self vectors of length 0. So, they will all appear at the origin. So, if I have a Patterson map plotted here for this particular molecule, we should have a large central peak corresponding to all self vectors. Other than that, now we have the opposite vectors 1 to 2. So, if the 1 to 2 vector appears here, the opposite vector of 1 to 2 will appear on the other side of the origin because it is just opposite in sign. Similarly, if the vector 1 to 3 appears somewhere there, then its centrosymmetric opposite will come here, that is 3 to 1. In the same manner, if 1 to 4 appears somewhere here, the corresponding 4 to 1 should appear at that point. Now, if we look for the vectors 2 to 3 and 3 to 2, suppose 2 to 3 appears somewhere there, so the corresponding 3 to 2 will appear here. 2 to 4, if it appears somewhere there, it will have 4 to 2 at this point. Then one can have 3 to 4 appearing at some other point, whereas the 4 to 3 will appear like that. So, what we see in this particular map, which is generated here, is a Patterson map which is centrosymmetric with respect to the origin. So, always a Patterson map is centrosymmetric irrespective of the structure, whether it is eccentric or non-centric. How many such peaks have appeared? We have 4 self vectors. So, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So, for a structure with n equal to 4, we have 16 vectors or peaks appeared in the Patterson map, of which 4 are self vectors at origin having the height maximum or maximum intensity, and other vectors appear at different locations with the intensity much less than the origin. So, the most useful feature of this Patterson map is the presence of peaks at certain positions, which we have drawn here, and this indicates the information about the symmetry elements present in the unit cell. So, the coordinates of atoms can then be determined from these Patterson maps. So, when we draw these Patterson maps for different symmetry elements, we have to draw them with their corresponding equivalent points. There are some useful features in this Patterson map. We have a few lines and planes which are of particular interest to us. These are called the Harker planes and Harker lines, where these vectors are located, that is, the atoms can, the locations of u, v, w are on those planes or on lines. So, the presence of these values at a given line or plane indicates the presence of a particular symmetry. So, if you have a two-fold symmetry parallel to A, B or C, then your vectors u, v, w will have values 0 v, w when it is parallel to A. When it is parallel to B, it will be u 0 w. When it is parallel to C, it will be u v 0. if it is a 2-1 screw parallel to A, B or C, you see here in this case there is a translation associated with the rotation. So these points would then change to half VW, U half W and U V half. Similarly, if there is a mirror plane perpendicular to A, B or C, the Harker sections will then become, Harker lines will then become U00, 0V0, 00W, or the A glide perpendicular to B or C will represent a Harker line like half V0 or 0 half W. Similarly, B glide perpendicular to A or C will generate the Harker line at U half 0 or 0 half W. Similarly, C glide perpendicular to B or A or B will generate the Harker lines at U0 half and 0 V half. So these are the corresponding Harker planes which are corresponding to the 2-fold and 2-1 screw axis, and these are the Harker lines which correspond to mirror or glide plane. So we will now investigate a few cases, simple cases with the Patterson synthesis. So our case 1 is a structure where we have one heavy atom per asymmetric unit in P1 bar space group. So as we know, in case of P1 bar space group, the equivalent points are x, y, z and x bar, y bar, z bar. So that means if we have one atom at x, y, z, the other heavy atom is at x bar, y bar, z bar. So of course, the largest Patterson peak is the self atom, that is atom 1 to atom 1 and atom 2 to atom 2, and these two Patterson peaks will appear at origin, that is at 0, 0, 0. The other two prominent peaks or other two major peaks would come or appear at 2x, 2y, 2z and minus 2x, minus 2y, minus 2z. See, remember, u is x1 minus x2. So here it is equal to x minus of minus x, which is equal to 2x. So v is 2y, w is 2z. In the same way, u prime is x2 minus x1, which is equal to minus x, so it is equal to minus 2x. Similarly, v prime is minus 2y, W prime is also minus 2z. So the peaks are appearing at those 2 points. So by looking at the Patterson map of a triclinic system and then getting the values of 2x, 2y, 2z, one can easily divide it by 2. One can divide it by 2 and get the values of x, y and z. So this is how one can get the coordinates of the heavy atoms in case of a structure where you have one heavy atom per asymmetric unit in P1 bar space group. So let us see if we have a situation which is my case 2. One heavy atom per asymmetric unit in P21 by N or P21 by C space group. So in case of P21 by C space group, the equivalent points are, as we know, x, y, z, minus x minus y minus z, x half minus y half plus z, and x bar half plus y half minus z. The vectors will be 4 into 4, that is 16. So what are those vectors? Let us try to get those vectors right for all these 4 systems, so 4 asymmetric units. So we write here the coordinates x, y, z, minus x minus y minus z, x half minus y half plus z, and minus x half plus y half minus z, and again we write the coordinates here as well, x, y, z, minus x minus y minus z, x half minus y half plus z, and minus x half plus y half minus z. So now if we assume that this set corresponds to x1, y1, z1, and this set corresponds to x2 minus y2, x1, x2, y2, z2, then what we will write in the blank space is x1 minus x2, y1 minus y2, z1 minus z2. So this matrix, when we write x1 minus x2 is 0, y1 minus y2 is 0, z1 minus z2 is 0. Similarly, minus x1 minus x1 minus x2, here it is minus x, so minus 2x, minus 2y, minus 2z. This one is x minus x is 0, it becomes half minus 2y and it becomes half. This one here becomes minus 2x, half minus 2z. So if we continue the same for the next row, it becomes 2x, 2y, 2z. This point is 0, 0, 0 because it is minus x and then minus of minus x is plus x, so it becomes 0. Then this goes for 2x, half plus 2x. Then here it is 0, half plus 2y, half. In the third row, this becomes 0, half plus 2y, half minus 2x half minus 2z. This point is 0 0 0, the origin peak, and here we have minus 2x minus 2y minus 2z. The fourth row is nothing but 2x half plus half and half plus 2z, 0 half minus 2y half minus 2x minus 2y 2z, and here the last point is 0 0 0. So now we need to look at these vectors carefully. These are all possible vectors for this particular space group P21 by C. Now, point number 1. The self vectors at 0 0 0 appear 4 times. The point number 2 is there are 2 appearances of 0 half plus 2y half and 2 centrosymmetric positions of this. So 0 half plus 2y half is here, and also 0 half plus 2y half is here. The corresponding centrosymmetry related points are these two, where it is instead of half plus it is half minus. The third point is that again there are 2 appearances of 2x half minus 2z and its I, that is center of inversion related positions. So this 2x half minus 2z is here, 2x half, this should be 2z, let me correct it here. So this is one point which is 2x half plus 2z. Similarly here it is 2x half plus 2z, and its corresponding centrosymmetry related ones are here, which is minus 2x half minus 2z minus 2x half minus 2z. And then in the point number 4, we can note that there are 4 vectors of the type 2x, 2y, 2z with different signs. Say for example, this is a 2x, 2y, 2z and its inversion related is minus 2x, minus 2y, minus 2z. These two are inversion related. Similarly, these two 2x minus 2y plus 2z is inversion related here. This should be plus 2y. If you correct it, because this is half plus y minus half minus y, half gets cancelled, minus y becomes plus y, so it becomes plus 2y. So what we have is the following. The number of separate Patterson peaks in the map are 8 except the peak at origin, four of them have the double height. As well. So in this case, there are different types of peaks at different location. So what we see is that we have some peaks of the type u half w, which are here. U half w is located at that point. U half w type of peaks. Similarly, here we have u half w set of peaks. This one is also u half w type of peaks, and this one u half w set of peaks. These u half w set of peaks represent a peak on a Harker section, and the peak of type 0v half, that is some things like that, 0v half, here it is 0v half, and so on. There are other peaks also, which is here 0v half. So these 0v half set of peaks are located on the Harker lines. So by identifying these peaks and getting their coordinates determined from the Patterson map, one can then calculate the coordinates of x, y and z from the various values of u, v and w determined from the Harker lines and Harker sections, and then calculate the position of the heavy atom. So once we determine the position of the heavy atom accurately, that information can be fed into the refinement program, and the phases of other reflections which were not determined before can be determined, and by doing a delta F synthesis one can complete the structure solution for the other lighter atoms. So, as a homework I would like to give the problem that you identify the vectors in Patterson map with one heavy atom. So, the assignment is like this. Identify the vectors in Patterson map with one heavy atom in the asymmetric unit with the space group P212121 and PBCA separately, and identify the Harker lines and Harker sections. In the next lecture, we will discuss about another case where you have two heavy atoms in the asymmetric unit in a case of a P1 bar structure, and then we will discuss one practical example how to use these Patterson maps and the heights of the peaks to get the coordinates of the heavy atom.